Ever wonder how electrons find their place in an atom? Well, in today's video, we'll find out. Welcome back, everyone. Get ready to explore how electrons distribute themselves in atomic orbitals using the 𝐓𝐴𝐷 principle and Hund's rule, which is quite annoying. But with that, we'll examine two different points of view of electron configuration. And in this question, we're tasked with A. Figure out the electron configuration in the notation of equation 5.44, which if you're following along is the same thing that you probably saw in chemistry with the s shell and p orbitals, things like that, for the first two rows of the periodic table, so up to neon. And check your results against the table 5.1, which again, I have the whole question copied into the PDF, so you'll be able to see that there. And then in part B, we want to figure out the corresponding total angular momenta in the notation of 5.45, which deals with Hund's rule, which is, as the author says, kind of a ritual, for the first four elements. And then we want to list all the possibilities for boron, carbon, and nitrogen. And let me tell you, listing them all is definitely a headache, so be very, very careful when we approach this. That being said, by the end of this video, you will clearly know how to view this electron configuration nonsense in two almost different points of view, and for totally different things, one dealing with how they're spaced out, the other one dealing with the total spins and angular momenta. So that's pretty cool. But as a reminder, before we begin, there is a free companion PDF for you to follow along with. All you have to do is access it using the link below. So, heading into stop number one, or part A of this question, we have to take a step back and ask ourselves, what is electron configuration? In which, the electron configuration describes the distribution of electrons in an atom's orbitals. The arrangement follows a specific order based on the increasing energy levels of the orbitals, which is governed by the 𝐓𝐴𝐷 principle, and of course the Pauli exclusion principle. Because we know that two electrons cannot occupy the same four quantum numbers or the same state. So since they're fermions, we have to be difficult, and at least that will lead to the fun in chemistry, as the author says. That being said, we know that we want the first 10 atoms here, or the first two rows. And of course, it'd be easy to just list them in a chart like this, and, admittedly, it'd be a lot easier for you just to go to something like 𝚃𝚒𝚘𝚋𝚠𝚠 and see how they configure their stuff on there, because it's a really great interactive online website. Definitely check that out because it does help. That being said, the atomic number, or Z, is what we're focused on in this text. So we're going to organize them like that. And as such, all the way up to neon, that's the first 10 elements. So all their abbreviations or the symbols and the elements they represent. Not too bad, we've probably seen it before. The key thing here is that the atomic number and the electrons need to match for these examples, so we just want to write them 1 through 10. Cool, we got that. Now, the interesting part here is that whenever we're trying to deal with the configurations, what we have to understand is that we want to label them in these orbital styles with S's, P's, D's, and F's. And interestingly enough, the author gives a great bit of history on this. Griffiths or Darrell, I can't remember who put it in. I'd have to reference the old book. But he tells us that S stood for sharp, P stood for principal, D stood for diffuse, and F for something else. I can't remember. But it was really cool to see the nomenclature come back into context of why they labeled it like these, as chemists like it. But to read these off, what we have to realize is that one electron can be in a spin-up state, which is what we're assuming in the case of hydrogen, back when we studied that in chapter 4. And so we know that we're going to be stuck in a half singlet state, and if you're in chemistry, you'll put an arrow up for that, much like we do in quantum mechanics in a singlet state. Cool there. But we know that when we have a configuration, we want to be in the first orbital outside of the nucleus, so our principal quantum number n equals 1, but of course if n equals 1, by the rules of quantum numbers, L has to equal 0. And when L equals 0, it corresponds to the orbital shell S. That's a pretty cool way to remember it. There's actually another really interesting diagram given by library text, something like that. I'll link them both below because they're both really helpful resources for this style problem. And they jump into how the S's and P's kind of integrate together and the directionality that they come with in the orbitals. Very cool stuff. That being said, when we go to the next atom up and we get to the helium atom, right, what we see is that, well, if I can have a spin up, then I can have a spin down because Pauli exclusion tells me I can't be in the same state. So what this tells us is that although N and L can be the same quantum numbers, I can complete the singlet state with one spin up, one spin down. And as you see, the power that I write up here on the parentheses is the number of electrons I have when added together. So I have 2 electrons based on the power in the first principal quantum number, and we're also in the first shell. Cool. We like that and we can deal with that. The next one we have to be careful of with lithium because we have 3. This tells us that we can't be in the first orbital, we have to go to the second. Hence, we add a 2, and we're going to be in the L equals 0 because quantum numbers don't go up to L equal 1 just yet. We're still trying to complete the singlet states first. So we have 2 for the principal quantum number, so that tells us we're in the second orbital shell. And S tells us we're still in the case of the orbital angular momentum number being 0. The difference is that with these two, we had MS being plus 1/2, minus 1/2, and it works and completes the singlet state. In the case of lithium, we only have 3 electrons, so if you add up the powers, we have 2 here, 1 here, and we get the 3 that we need. Then we get to beryllium, we can still fill out this s orbital and get to, with ms equal 1/2, ms equal negative 1/2, so we have 2 and 2 electrons, that gives us 4, we're good to go. And if we just keep this going, we can now see that, wait a second, I have the energy capacity to go to a p orbital. And that tells me that based on quantum numbers, let me get my pen out, we had n equals 2, so L could equal 0 or 1. And with that, we know that we're going to have a case of 3, or what in this case, 6 different L equal 1 operations, because if L equals 1, that tells us a lot about what ML can equal, which is plus or minus 1 and 0. And then for each of these, we can have the MS's, which could be plus or minus 1/2, plus or minus 1/2, plus or minus 1/2. So with 3 of these, each with 2 different possibilities via Pauli's exclusion principle, we can have up to 6 states in the L equal 1 case. Pretty cool. That being said, we have 8 total states for n equal 2, and that falls right in line with what we expect. And so all we see here is that we need to fill out the p orbitals in ascending order. So, and what I liked about the library text, whatever it was, they show you how the organization of the orbital starts to space out, meaning that we could see that the directionality of the p orbitals makes a difference. And we will come back to this because when we get into the p orbitals for the other configuration style, we need to understand what the electron or what the direction is so that we can account for the angular momentum direction. Very important there. But without further ado, we see that S corresponds to L equals 0, P corresponds to L equal 1, and we see that we get a cascade of other ones based on the quantum number rules, and we can just pump them out and finish them off. And we see here that by the time we get to neon, we fill out all 3 directions, and one lobe and the other lobe in all 3 directions. So we get 6 plus 2 plus 2, that gives us the 10 that we need, and we're good to go. This one's pretty easy once you just start repping them out a couple times. It gets really weird when you have to go up to another energy level in the D shell, and then you have to go back to the lower level P shell, but you'll get the hang of that. Definitely check out P table, it's a great resource. But now let's dive into the crux of this and finish off this part A. That being said, problem checkpoint, we saw how to deal with configuration 1, and we're good to go. Let's dive into something a little more nitty and gritty and deal with the total spins and angular momenta. Alrighty, heading into stop number 2, we have quite a handful to deal with, as you could probably tell instantly by looking at the table. However, there are a couple rules here that tell us what we can do and what we can't do. Let's recall that the first four elements both occupied complete singlet states for each cell level. So that being said, if we're looking at the amount of spin total in hydrogen, remember that we only had one electron, so the amount of spin was one electron had a half spin, so we're good there. But also remember that we never went to a p orbital, we only stayed in an s orbital, so L would equal 0 here. That being said, J is the total of all the angular momenta, spin and orbital angular momentum. And what we see here is that when we add these two together, we get 1/2. And when we put this J equal 1/2, here we see that we get a 1/2 on the bottom as the notation for Hund's rule would suggest. And we see that S is, that the capital L here for the total angular momentum gives us in the first orbital, so 0, and that would replicate the S shell. So cool, following the same kind of rules there, no big deal so far. And then because S equals 1/2 here, the total spin, we have it to where we have 2 times 1/2 plus 1. So that gives us 1 plus 1, and that's why we have a 2 over here. By the way, if you're typesetting this, it can be cumbersome and a little annoying, so don't freak out too much whenever you see this stuff. Just be aware that writing it does get rather cumbersome at some point, so be cautious with that. Now, as we get to helium, we have something slightly different. We now have a full singlet state here, so a spin up and a spin down. And if we remember m sub s, that's plus 1/2 minus 1/2. You add the two electrons together, you get 0. So they offset each other. And then we have still in the same first shell, so L equals 0. Therefore, the total is 0. So we have to replicate this here. 2 times 0 gives us a positive 1 up here in the red. We're still in the first shell, so we're S there. And we have a 0. Cool. No big deal. Now, what we have to do is be very, very careful with how we start to incorporate the next level of this stuff. Okay? In the case of lithium, we have 3 electrons, so we know that we're going to have a plus 1/2, minus 1/2, plus 1/2. So that gives us a total of 1/2. Again, whenever you see capitals like this, the author really nails down the fact that this is for totals. Not just what happens with individual electrons, but all of them summed together. And what we're looking at here is for the case of L equals 0. Okay, because remember, we're not going into L equal 1 yet, which will then open the cascade doors for M sub L and then the M sub S's for each of those. So for lithium, we end up with another 1/2 in the total. So we get the same replicated state here as hydrogen. Now, this is not what the electron configuration showed us in the previous notation. What it does show us is the spin state totals. That's what we're after, and that's what we have to be careful of. Moving on to beryllium, we see that we have 2 complete singlet states. So when we see this, we have 2 complete singlet states. Awesome. We're ready for that. We're happy for that. Now we get a little more crazy with everything that could be an answer. Okay? So with this, we had to be a little careful. So we know that for boron, where we have 5, we're going to have a net spin of 1/2. Okay? Cool, that's easy because plus 1/2, minus 1/2, plus 1/2, minus 1/2, plus 1/2. Cool, we can deal with that. Now, the arrangement rules for quantum numbers, as discussed back in chapter 4, I think it was 4.148 is what he referenced. I don't remember. I'll have to show a link for that. But the selection rules tell us that, and I should have put a 1 and 0 there. Go back and edit that in now. 1/0. So with these selection rules, we know that we could be, in addition to that 1/2 plus the 1, or the 1/2 plus the 0, for all possible states it could be in. And that's what we have to be careful of in assessing these things. So with that, what we see is that if I have 1/2 plus 1, I get a 3/2. If I get 1/2 plus 0, I get the 1/2. And because I am looking at the 1 state here, and the selection rules allow me to therefore be in the p orbitals, we can go ahead and clear this up and show that we're going to be in a p-style orbital because we're of the angular momentum 1, again integers here, And the selection rules tells us that we can add up to this and minus up to, and then minus that as well, because we're in the magnitude. So we get these these two possible total spins or total momenta, and we can plug this into the form here. Again, just be aware that the form matching needs to go with the L and the P's here, things like that. You just have to be really careful when diagnosing these things because it gets really hectic sometimes. Be careful. And especially when we get to carbon here, right? And we say that for carbon, the two p electrons could combine for an orbital angular momentum of 2, 1, or 0. Okay? That's possible, for sure. And then the spins add to 1 or 0. Okay, cool. We have 6 of them. So we can either add the two other ones that are not completing the triplet state that they were supposed to be in, right? That are just hanging out there because remember, after 4, the first 4 occupy 2 singlet states, and then we have 2 more roaming around in the p orbitals, and they can combine in different ways too. So with this, we see that we can end up with a total of 3, 2, 1, or 0. And so with that, we have all these various arrangements based on 3, 2, 1, or 0. Clearly, if it's 0, we go to S. So as you can see, with 1, if we have 0 spin here, then we end up with a 0 here. If we have a 1 spin, then we end up with a 1 in the blue and a 3 in the red. Okay, makes sense. Now if we move on to the case of 1 orbital angular momentum total, we get to the p states here and all the different arrangements that could happen with spin and the total angular momentum j there. And then for the final, we're running out of combinations here. We could run into where orbital angular momentum totals could be 2, and that's where we go to the d state. And, again, this is all just a bunch of headache if you're not aware of all the combinations that quantum numbers can give you. And the only reason that that matters is because what happens when we excite or have any kind of like line series that we want to investigate, we have to know kind of where they started in the spin configurations. So very annoying to deal with in writing out all these possible combinations, and it only gets worse as you get more electrons. As you see, we had 1, 1, 1, 1, and then we got to 2. Then we got to 2, 4, 6, 8, 10, and then we got to too tired to count. So just be aware, they do get a little annoying there. And then for nitrogen, when we have 3 other electrons if you're following along on P table, you have a spin ups or the up arrow, up arrow, up arrow. So each one of them is following in a different orientation in a different not filled state. So the triplet states are not filled at all. And that being said, you can lead to a total spin of 3 halves or total spin of 1 half. So I could have 1 half, 1 half, 1 half added together to give me the 3 halves because we're all in 3 different directions. So that could be possible. Or I could have 1 half, negative 1 half, and then 1 half again. That gives me the positive 1 half I see here. That being said, all of these could add to the integer orbital angular momentum numbers of 3, 2, 1, and 0. And then, of course, if we add the two together, we get 5 combinations of total angular momenta. That is a lot to keep track of. And then, of course, as you see, each criteria leads out to this. Very annoying. Definitely feel free to fact check this for yourself with all the possible combinations. And when you do so, I think it's now important to reference some of the diagrams given by one of the online texts that shows you how S goes to 2s goes to the p orbitals, and those p orbitals all have the different orientations. Very good to check that out. While this was long-winded, I think it was important to show that this goes back to the combination and selection rules of quantum numbers. And if you don't remember those, I might just make a PDF or a sticky note for those because they definitely come back in full force and full vengeance here soon. Definitely be aware of these. Definitely get ready for them. And if you need more practice, P-table and Hund's rule, there's plenty of worksheets online where I could just put more of these problems on. They're very fun, very kind of confusing at first, but once you get the hang of it, like I said, you're good to go. That being said, we reached our second checkpoint here, and we now get to see how these are 2 different points of view of the electrons in the atomic structure and why we need to kind of investigate all of them. As you see, this is setting us up later in quantum theory where we get to deal with kind of structures, and with those structures we can see groups. From those groups, we can make abstractions, and those abstractions lead to wonderful, maybe saying coincidence, maybe not. It's just a wonderful set of how these things correspond. And if you like particle physics, Murray Gell-Mann wrote a nice passage about group theory and several physics or mathematical physics books. And he loves group theory. And guess what? The next chapter is about symmetries and conservation laws, so it will be fun to nail that down. But with that, let's head to concluding remarks because this problem is done. It was a little shorter on the computational side, but a little longer on the explanatory side. So definitely get these ideas in your head because they will be explored again soon. So thank you everyone for watching and dealing with my rambling as I get excited about these weird things. A massive thank you goes out to our patrons for their invaluable support, making all of this possible. I see that the articles and supplemental stuff with resources has been gaining a lot of popularity. So I'll keep posting that because learning is supposed to be fun. It's supposed to be helpful. If you need help or want tutoring, things like that, please go to the Patreon and we can work out a course or schedule. It's all about having fun and understanding, and the rigors of school might not make that possible when you're just trying to get through a test or homework. So let us know. We'll be glad to help. That being said, please consider subscribing and sharing to fuel this curiosity or even becoming a patron yourself. All the support is helpful, especially with the way that we're progressing in momentum ourselves as a channel and team. It's been a lot of fun and a lot of insightful feedback, so thank you for that. New content is posted weekly to aid you in your curious pursuits and slight deviations to the course, but sometimes it's worth traveling down some of those rabbit holes and going in a different exploratory route. Books, notes, and other reference materials are found below. Follow it with the Patreon link. And if you have any questions, please feel free to reach out. Again, learning is fun. As always, thank you for watching, and until next time, stay curious.